having seen the vertical composite breakwaters, now we will go into the horizontal composite breakwaters. The wall of the vertical composite breakwaters suffers damage, because you see that although it is a gravity type of structure, it is resting on a rubble mound base. But if there is excessive force acting on this structure, there is a possibility that the overturning can happen and it can be a sudden instant failure. The entire caisson can overtop or over a period of its existence it can have some kind of problems, and you need to have possibilities or look into the possibilities of rehabilitating the caisson. So what is meant by rehabilitation of this? So you need to have some kind of method to reduce the forces that is coming on the caisson. One such possibility was having a perforated breakwater in front, which we have seen earlier. The other aspect is to have some kind of rubble mound, completely fill it with rubble mound, so that the forces will reduce, the forces coming on the caisson will be reduced. So you still have a calm pool of water, or tranquility can be established, and then you can still use it for berthing of vessels. So here in this case, without this, it is called, you have a rubble mound on bottom, so it is called vertical composite breakwater. When you have some kind of rubble on the horizontal direction in order to resist the horizontal force, then you have, it is called as the horizontal composite breakwaters. So the Mormugao port in India is formed by such principle, and which we will be seeing soon. So this Mormugao port harbor, Mormugao port harbor is more than 100 years old, and these are all constructed by mass work, as you can see here. So this is a mass work, and this is the lee side, and this is the sea side, and since laterite blocks are available in plenty, so they have adopted laterite blocks here, and this was the configuration. Without this marked in ash color, grey color, this was the original composite breakwater, vertical type composite breakwaters, wherein it was serving its purpose. And you see that this width is about 9 meters, and minus 9 is the bottom of the composite breakwater, that is the levels, and all the other levels are also indicated here. So in due course, actually the design wave height for this is 5 meters. But over a period, what happened was that they experienced a lot of overtopping, and this started giving some way, because the loading coming on the caisson was quite high. And then what they decided is to drop in wave breakers. Wave breakers are wave breakers are just kind of blocks each weighing 12 to 18 tons. They used this laterite blocks and converted this vertical composite breakwaters into a horizontal composite breakwaters. And in fact, we have done some studies on this, because even after having this absorbers of this laterite blocks, which are weighing between they had only two classes, one is 12 tons and other kind of blocks were weighing 18 tons. So these blocks were installed and a slope of about 1:2 was formed, and this was giving a certain degree of relief for the caisson, but then still they could not come over the problem. So this problem was referred to us, and then we did simulate the exact the whole breakwater, and then did some calculation, did some experimental investigation through which we have made some recommendations which will come, we will see later. Is that clear? So typical cross sections of horizontal composite breakwaters are shown here. It can be having a single core, as you can see it is just dumping the laterite block, similar to what we saw in the case of Mormogava, because there was no core layer or secondary layer, or you can have a kind of a core layer as you can see here, and this is just dumping of stones, and similarly you can have a secondary layer over which you have the primary layer being dumped. So these are typical examples for the horizontal composite breakwaters. Now moving on to special type of breakwaters, some of the special type of breakwater which can later, after its continuous existence, it can become a standard breakwater. For that matter, even the rubble mound breakwater, once upon a time it should have been a new kind of structure, right. Slowly there has been improvement, and then it becomes, for example, your berm type breakwaters or the S type breakwaters. Berm type breakwaters is this. So this was initially it was so this is the wave. So we had initially only one single slope. Now you have a berm here, and in fact you have multiple berms also in certain cases. Okay, composite slope breakwaters. So the special type, for example, the perforated caisson breakwater has become widely popular, that it is considered as a standard breakwater as of now. Now common special type of breakwaters are non-gravity types like piled, floating or pneumatic types. So now this will just take up all these things. Now look at this curtain wall breakwater. Curtain wall breakwater, these can be used for small craft harbors, to protect small crafts. So you have piles, it can be over a rubble mound, or without the rubble mound also you just have some cover protection here, and it can have piles, and then you have a skirt here. Skirt in the sense, if you look from this end, how it will be, you have the piles and you have the skirt. This is the skirt. Okay, the skirt can be as less as possible. Maybe this is going deep into this is the seabed. Okay, so this will be the only the gap through which the energy can move. Okay, because of this obstruction, most of the energy is getting reflected back. So the energy which will be escaping through the under the skirt may be less, and hence this can be used as a skirt breakwater. In fact, you can also have this kind of a breakwater with moorings. So temporarily you want to have some kind of a calm area within the shallow areas, you can just have this fixed through moorings, and then when you want to transport it, you can just remove the moorings and shift it. You understood? But this can relatively, it is quite effective but particularly in short period waves. In the case of locations where the wave period or the wavelength is less. Why do I say that? So for example, if you have a long period wave, this will easily penetrate through under the without getting attenuated, without the amplitude getting attenuated, this can simply move. Understand? Whereas if the period is short, it can get attenuated when it is going and hitting the structure. You understand? These are all some of the considerations which you need to take into effect when you are planning for any kind of a breakwater. Now this is the sheet pile. So these are more or less these are fixed type. In the case of skirt breakwater, you can either have it as a fixed pile, or you can still have it as a floating type. You can easily modify that as a floating type, but here this will be a continuous sheet pile, that is the sheet pile is running perpendicular to the screen, you understand. So this is going to be quite expensive. There are other associated problems. If you do not have a proper toe protection near the sheet, you can have very deep cover taking place, because it is a abrupt a solid obstruction. So you can have anticipate significant cover, and the founding level has to go well below, so that the much below this covering depth, so that it does not lose its stability. So this is also quite expensive, and also you have corrosion problems, all those things. So we need to carefully look into these aspects. Then comes horizontal plate breakwaters. So here you have a horizontal plate running over a distance, over a length. Now the length of this breakwater certainly has to depend on the wavelengths. So in a location where, again, if you have a long wave and then you have a horizontal breakwater like this, then there is a possibility that the wave will just go through this horizontal plate without getting attenuated, you understand. So there are some guidelines for designing this the length of the breakwater. So the idea is, it is going to destroy the destroy the particle orbital particle velocities when the waves are propagating in its direction, and thereby offering enough degree of attenuation. So a careful understanding of the length is one of the important aspect. Length in the sense, length of the length of the horizontal plate breakwater in the direction of wave propagation. Okay, and I just would like to make a passing remark that horizontal plate, there is one concept wherein horizontal plate breakwater can be used as an energy converting device to convert the energy contained in the ocean waves into meaningful electrical energy. Okay, there are some attempts. So you have to the moment you put horizontal plate breakwater into the internet, I am sure that you are going to get some information about that. So the person who has worked is on Professor Graf. So he has also done some work on this horizontal plate breakwater. So that will give some. You can just go search for horizontal plate breakwater has wave energy converter. So you are bound to get some information on these aspects. Then comes the floating breakwater. Floating breakwater usually has a floating barrier. The concept is same as the earlier case, wherein you have a horizontal plate, but this is now extended. It's something like a floating barrier. So it can be used for floating bridges, etc., and also for mooring, for berthing of small craft vessels. So the whole thing can be used for berthing of vessels on the lee side of the breakwater. And again, the width of the breakwater is quite important, and this type of breakwaters may not be so effective at locations where you have long period waves. As I have said earlier number of times, the long period waves, what happens, it pulls the structure to the extreme end. Okay, so then your cable, your mooring cable is going to be beyond the tension, allowable tension, and there is a possibility of breaking of the mooring line. So these are some of the problems you need to consider. But another thing is, when you have a floating barrier like this, what is the kind of energy dissipation that is likely to take place? What are the physics which is going to take place? The one is the destroying or reduction. I would not say destroying, although I am writing it here. It will be decreasing okay, or reducing the water particle kinematics, okay. So it reduces the water particle kinematics, thereby you have energy being less and less by what, because of the barrier, because of the obstruction, okay. But because if you have a solid obstruction, you should know that there is going to be certain, when you have a solid obstruction like this and the waves are going to come and hit the structure. So this is your floating breakwater. So when the wave is going to come and hit the structure, you see that this is going to be, if it is going to be a solid structure, then you are likely to have reflection, and when there is more of reflection here because of the vertical surface, then you see the forces exerted on this structure is going to be more. When the structure is going to experience more force, then the mooring line also becomes a big, the mooring lines have to be taken care of to take if you want to maintain the stability, the force has to be, the mooring line has to be designed for the maximum force that is likely to be the breakwater is likely to be subjected, alright. So the other possibility, the efforts were to create some kind of a porous medium. You still have a structure like this, but then allow the one thing is, when you have something like this, then you have the same principle, plus in addition the dissipation can be because of the waves running through the porous medium. You understand? We have already seen that that is the principle on which your rubble mount breakwater is designed for, right? Is that clear? So these are all some of the concept, and there were a lot of efforts that has gone into in order to make this floating breakwater. The concept of floating breakwater started as early 1940s during the World War, during the invasion of Normandy. That is the time when the concept of floating breakwater came into existence. Floating breakwater has its own advantage, but it certainly has its certain disadvantages. Particularly it is not that effective in attenuating long period waves, okay. Then you can have a number of units also depending on your need, okay. So realizing some of this in concept, one such concept was, for example, there was one type of floating breakwater which was called as wave maze. What does that mean? That means that you have the used tires, and these tires are just inflated with some kind of a material, and so that to promote, to enhance the flotation. So there are some kind of material which can be injected within the tire so that the whole thing can float. So you can, so the people what they did is, they did like a number of tires linked together, as you can see alternative. This is in plan, Now in section you can have tires. Here this is, I am talking about tire, okay. So here you can, they tried about 3 or 4 tires, because this depth of submergence is also important for you to for the breakwater to attenuate the energy. So in this case the energy is dissipated through the porosity that has been created because of the tying up of a number of tires together. Is that clear? So there has been a lot of other works also, having a floating breakwater with a skirt, a number of skirts, etc. There are different configurations have been tested, and their efficiencies are all available in literature, and you can look into some of these aspects. Okay. Now, having being exposed to some of the basic types of breakwater, now we will let us go into the breakwater alignment. The alignment of breakwaters for formation of artificial harbors is arrived from the prevailing wave characteristics of the site, in particular its direction. That is true because, as I have already told you, the orientation of the breakwater has to be normal to the predominant wave direction. That is very, very important. Without knowing, without having a knowledge on the wave direction, it is impossible for you to finalize the alignment of the breakwater. So, this is often done either through numerical modeling or by physical modeling. Earlier days it used to be mostly physical models, through physical modeling. Now, these days I think maybe from mid 80s, ever since the computers, the progress in computing facilities increase, people have resorted to numerical modeling. There are either this or that, both has its own benefits and drawbacks. Because adopting a physical model, a scale model for a physical modeling for this kind of a problem sometimes is a big difficult, because you should know what is meant by distorted and undistorted modeling here in the case of distorted, undistorted. I am sure that you would have heard in your beta course when you are talking about geometric similarity, all those things, right. So, we will also be talking about those aspects later. So, that is when you want to model a basin, and your wave basin is, say for example, it is 20 meters or 18 meters by 20 meters in your lab, okay, and you want to model a distance of about 2 kilometers or 3 kilometers of the shoreline, okay. So, you cannot do that with the kind of scale which you have, and your wave height that can be generated maybe maximum is 20 centimeters. So, the vertical scale has to be definitely different from the horizontal scale. The vertical scale you are talking in terms of 20 centimeters, whereas the horizontal scale you are talking in terms of 3 kilometers. So, you are forced to use a distorted model. Sometimes this may give some problems. Another thing is, if you want to include the sediments, then it becomes a very difficult thing. That is a problem both in numerical as well as in physical model studies. Well, I will not go into all those complete details. The typical layouts, considering the character of wave directions distribution and shoreline, are shown in the next slides. For example, a port alignment, a port selection and the breakwater alignment for narrow wave sector, that is you have well defined wave directions throughout the year. If it is very well known direction, almost 100% predefined, then as in this kind of a configuration. So, you see a headland, and then you see that adjoining the headland, if you come across something like a bay formation, wherever you have bay, it is an ideal place where you can think of stable bay. It is there is a possibility for you to develop a port, and of course there are other aspects we need to look into. So, in this case you see that the waves mostly come in this direction, and hence the alignment of the breakwater can be in this, in order to take care of the effect of this breakwater, okay. So, how long this has to proceed, maybe here up to this, okay. All these things you can do with the numerical modeling by combining the effect of refraction, diffraction and reflection, and running your numerical model and also optimizing your breakwater alignment. Is that okay? All of you are with me? Now, here the port selection, when you have a wide range of wide sector direction, when the waves come from both directions, then in this case we go in for this kind of harbor, okay, both of same length, so that so we do have some such kind of configuration even in India. So but this is not a port, maybe a fishing harbor to the best of my knowledge. There is an which is called as Arokyapuram. I do not know if so this is a small for I mean landing of small crafts. We have had this kind of a layout. Now you can have something like this, where you have large littoral drifts moving in. So these are all broader aspects. When you have one side predominant wave direction, but at the same time you have the other side less direction. So for example, you have a coast wherein you have about 60% of the time the waves are in this direction, maybe 65% of waves in this direction, and 35% of the time the waves are in this direction. This is one of the maybe an example of our east coast of India. So what will happen then? Naturally you need to have a breakwater in this direction, which will be definitely longer, okay, and this if you leave it only with this breakwater, then the other months you will have problems. So what you do is, we need to have one more breakwater here, then this breakwater can be something like this, okay, smaller in order to take care of this direction. So all these things need to be designed properly. So you need a good amount of area here. It depends on what exactly you are planning for, whether it is a fishing harbor, commercial harbor, etc. And then so this is just a broader idea concerning the alignment of breakwaters. Now there are different types of breakwaters. This information is given by Professor Herbisch. He has brought a good handbook in coastal engineering. I wish if you have the time you should look into this book also. It gives a lot of other information on the behavior of waves and associated aspects. So here you see that you have different alignments. So for example, similar to this, a longer breakwater and a smaller breakwater, and then you have this constructed in near the mouth of a river, wherein this is also very common, wherein you have you have a opening here. Remember in the case of Pondicherry port, we have seen that it is lying inside the river, right. So you have a river, and then the river will go inside, and then maybe you have some wide area here, the river will be going here. So this area is now developed as a port, okay. So in order to make sure that the vessels the enough draft is maintained here, and so this will be having a training wall, okay. That is what is shown here. It can be either this way or the type of what we have here, and then it can be like this, almost the same direction. This is some typical of a training wall, and a bit rare, this is a bit rare, where you have two breakwaters, and then in between there has another one breakwater. And you also have to recollect, when we had the lecture on what is that, we saw the lecture on I forgot. Remember we saw the lecture on the coastal protection, where I had mentioned about Kakinada. Remember formation of Godavari spit, and then the spit extended, and then the spit itself was acting as a a long breakwater, so that we now in that case we had a free breakwater caused by nature. And only thing is, what happened was the breakwater, something like this, the spit was growing, and then we needed to construct only one breakwater here, because you did have some amount of disturbance because of the waves coming from this direction. Okay, please recollect, or you can go through the lecture, my lecture on the Kakinada port, on this one. So typical layouts, other typical layouts taken here and there are looking like this, as you can see here. For example, here although this itself is offering certain amount, a certain degree of tranquility, you need to, if you need more tranquility, then they have extended the breakwater like this, so that the tranquility in this portion increases. Now probably this would have been a harbor wherein they would have done the layout analysis, everything, and then once after execution probably they would have still felt that there is a need for increasing the tranquility. In that way, looking at different alternatives, they would have decided to have a breakwater here. You understand? This is something to shield before it reaches the harbor entrance. Is that clear? So this is a typical layout of a Tuticorin port, which is situated south of Indian Peninsula. So you look at one of the longest breakwaters, and it is around 4 kilometers, the breakwater is around 4 kilometers, but here we do not have much of problems concerning the sand movement. This is mostly for the tranquility. Okay. So these are all some of the pictures about this cross section of the southern breakwater of Tuticorin port. So quarry stones, they have used average weight is about maximum weight is 70 kg, and some of these things have been adopted. And I leave this, all the materials are available, so you take your time to look into this details. Okay. So here you see that 6 tons stone is adopted for the seaside. Okay. So usually you cannot just take it for granted. Usually it is around about 3 meters water depth, up to about 3 meters water depth. Your weight should be around 2 tons, but you cannot, I do not want to generalize this, but it gives you some kind of an idea. Between 3 to say 5 meters, the should be around, I would say about, maybe I would go further, 1 to 2 tons approximately, and maybe from this one maybe around 1.75 to 2.5 tons, maybe even 3 tons. Okay. Up to about 8 meters, you can you should have something like around 4 to 6 tons. I would say I will reduce this 6 meters, 4 to 6 tons. So these are all approximate guideline, but you need to calculate using the Hudson's formula or the Vandermeer's formula to calculate all this, the weight of the stone. Mind you that the fixing the wave height is extremely important. You have to take utmost care in finalizing the design wave height for the breakwater. Now selection of breakwater, since we have so many options, although we have a number of options, but it is a normal tendency that we think of sloping breakwater. Sloping breakwater, it is easy to construct, but there are certain disadvantages which I have said, because the base width is huge and it occupies more of its footprint is more. Okay. And it is really, it looks very massive. and if from aesthetic point of view it is not good. Okay. So now depends on selection of breakwater type, depends on environmental conditions, construction and maintenance costs. Your construction equipment is very important, type of labor, skilled or unskilled, then material availability. See, for example, if you are talking about a breakwater, developing a fishing harbor, a small fishing harbor, wherein the breakwater need to go only up to about say 3 to 5 meters water depth, okay, 3 to 5 meters. So it is we are working really in very shallow waters, wherein the draft of vessels, but the depth you need for the harbor to be maintained may be maximum of 3 meters. Then the construction can be from on land, you can use just a tipper, and then you can just small cranes if you want, then cranes are definitely needed. So you just have to use the end on method, that the construction will start from the road side, from the road, and then you keep on progressing as you proceed. Okay. So in that case it is more easy for us to go in for rubble mount breakwaters, because skilled labor is not needed for this. Okay. Skilled labor is not needed, and many minimum equipments needed, not very sophisticated equipments, because you at the maximum you may need a crane. Cranes are having different degree of sophistication. Okay. A crane, the most important, one of the most important is the boom length. So you have a breakwater, rubble mount breakwater. Say for example, as I said, maybe this is 4 meters for a fishing harbor, for example. I am talking about a fishing harbor, and then in that case, if you are having a water depth of about 5 meters, see the boom length can be, so this is 1:2. From here, if the crane is there, what is the boom length? It has to place the toe also, right. You know, we have seen that now this is 5 meters, now the toe has to extend for another 3 meters from here. So from this end, this is the distance, 3 plus this distance, okay. So maybe about 15 meters maximum. But same thing, you imagine that you are running in at 10 meters water depth, then your boom length becomes more. So and getting such a kind of a crane becomes bit difficult. So all these aspects have to be looked into before you really get started with the construction. So selection under this where you have good rocks and large blocks available, that is the area where you can just simply go in for this kind of a breakwater. Where HS is less than, these are all some guidelines, okay. HS is less than 3 meters, type S. In case HS, the significant wave height you are considering is more than 3 meters, but water depth is less than 20 meters. In fact 20 meters itself is on the higher side, okay. But it does not matter, because there are so many breakwaters which are constructed even up to about 20 meters with S type breakwater, and this is usually associated with a superstructure, okay. Superstructure in order to take care of the overtopping, understood. Then if the HS is between 3 to 6 meters and water depth is greater than 20 meters, then you still sometimes think of going in for type S with superstructure. Sometimes it may be quite expensive, so in which case you might have to go in for special type of breakwaters, maybe a vertical composite breakwater, okay. So if it is greater, type S with superstructure or composite breakwaters etc. can be thought of. Good rock available, but blocks are not large enough, type S armor layer must consist of concrete blocks, because good rocks are available. This happens in many of the projects. Many of the projects you may have rocks of smaller size from the quarry, but when you want to have a large size boulders, it may be very difficult. And another disadvantage is if the individual rocks are greater than about say 6 tons, it is very difficult to transport also, because you have to transport it from the quarry to the site. Naturally you have to use the existing infrastructure, the roads. So this is going to lead to a lot of complications concerning when it is being transported around cities, within the cities. So what happens if the individual block which you want to use for design of breakwater, for construction of breakwaters, which are greater than 5 tons, then probably the best way is to go in for concrete blocks, because concrete blocks can be cast in on site, then just use it. You need a mold and then you cast the whole thing and then just install it. Good rock not available, but foundation is reasonably good. If the foundation is really very good, then the ideal one would be to go in for vertical type for water depths less than 15 meters, but for water depths greater than 15 meters you just simply go in for type C. Type C is what? Composite breakwaters. Type V is vertical breakwaters. Okay. Is that clear? Foundation not reasonably good, then it is better you go in for type S. If the seabed is of we have come across one area where you have some kind of loose sand under the seabed, and if you are forced to construct a breakwater under such environment, it is better to remove the entire material, although it is going to be very expensive, or have a kind of a special treatment to improve the strength of the soil and then start installing the breakwater. So bad weather all the year or rapid change in the wave conditions, caisson type V. Bad weather several months, caisson type V. Offshore breakwater with berthing facility on the seaside, on the lee side of the breakwater, caisson type V. Then short breakwaters you can go in for, short breakwaters maybe for fishing harbors, etc. Again this is the same thing, type S. If labor is cheap but skilled, sufficiently skilled, then you can very easily go in for caisson. If high labor and low cost equipment, you can think of rubble mount. So ideas of new concept of a new type of breakwaters by Bureau of Ports and Harbors, that is mostly in Japan. So where you have this picture itself gives you an idea again about the different kinds of breakwaters that are some of them have been constructed, some of them are still on paper. These are all some kind of concepts. The concepts, looking at the concepts itself, you get a clear idea, because one of the main idea is you should not have vertical face on the seaside. Another idea is minimize reflection, but at the same time absorb energy. So if you look at this basic ideas in mind, so that is why you have the perforations here, you have this kind of configuration so as to dissipate the energy while the waves are running over this curved surfaces, okay. Or you have some kind of holes here, perforations again, slits, these are called slits, slit type of breakwaters. Then you have different shapes, sloping or semicircle or perforations here, all these things. Mostly it is just to that is, if you construct a vertical wall, it gives an idea that you are trying to be greedy. Greedy in the sense you are trying to absorb the entire energy, but what happens is it is not absorbing entire energy, although you are trying to absorb the entire energy, you are allowing the forces coming on the structure to be more than 2 or approximately twice the energy that is contained in the waves. Later when we look at the wave forces on coastal structures, you will see that the amplitude on the wall, if the wall is impermeable, becomes 2 increases by a factor of 2. So these are all the concepts wherein you can have create some kind of permeability by having slits, by having a number of piles grouped, etc. So all these things automatically gives you an idea that this concept can be used as a breakwater. Is that clear? So a few more different, and these are all basically pile supported structures. So you can go even for water depths beyond about 20 meters or slightly more than 20 meters. So I will stop here and then we will go into the recent developments in breakwaters in the next class.